All right, good morning everyone, welcome. So first of all, who of you did cosmology? Okay, so one didn't. Okay, no problem. Who of you did it last semester? Okay, a large fraction. In fact, I see familiar faces. Good. Okay, don't worry if you haven't done cosmology. I will start with a little recap with the key core concepts that are needed. And when we are going to treat all the topics of the lectures, they're going to be self-contained. Okay, so I should explain all the concepts that are needed. If you are, the thing is that you are missing the overall picture. Okay, so I would strongly suggest you to look into the lecture notes. I will place them, like, let's say, the standard cosmology lectures on the web, and then I suggest you to go through them to have a broader picture. Otherwise, we are talking about things and say, okay, nice, I understood how dark energy works, but what is it for, how it plays with other topics, and so on, okay? Also because I will mention all the concepts during the review of cosmology, but I'm not going to explain everything of it, okay? So I will assume that you know the very basics, so, okay. Said that, let's start with a little bit of overview of what the lectures are going about and how they're going to be structured. So the first lecture starts today. You are here so you know where to go, and you also know the time, so no need to explain more about that. In the afternoon, there are going to be a seminar. We are already starting with that today. Okay, so today there is not going to be any scientific discussion, but I'm going to tell you how they are structured and what you're supposed to do. Plus, since you are going to present various topics that are taken from the scientific literature, so I'm going to provide you a list of literature that you can pick up, plus you can also pick up your own papers, okay? So you can, if you see something interesting, maybe we can discuss a little earlier if the topic is worth to be, it fits into the overall discussion or not, if it's worth to be discussed or not, because not all papers are worth to be discussed, okay? And then you need to present it. So I will just give you a few hints on how to present scientific topics and how to deal with scientific papers, okay? Because as I said, one has to be careful and pick them up, because there are like published 100 per day, okay, regarding astrophysics and cosmology. So one needs to be a little bit picky and choosy in what to read and what not, okay? Then your presentation, so once we'll start not right away, because of course we need to go through some advanced topics, okay, in cosmology, such that you have a better grip about all topics, and then the first one where you're going to start the presentation is going to be in June, okay? So the first one will be on the 7th, and then every Friday, according to your schedule, because then I will post the available dates, and you will have to pick up your own date, okay? So in the next weeks, we are going to fill up the schedule of your presentations. Then if there are changes to be done, I think no problem. We can just discuss, you can discuss between yourself, look, let's swap the dates and so on. So this is, I want to keep this flexible and up to you, okay? So there are going to be the slot. I'm going to prepare a page in which you can put your privileged date, but then you can change it among themselves if this is needed. So that's the list of topics that we are going to discuss. All of these things should be kind of familiar to you. So if you did cosmology, you already know what I'm talking about. So I'm going to be a short recap, as I mentioned, such that everybody, and you also did cosmology with me or other people, such that everybody is on the same page. And if you don't remember something that was discussed during the recap, you understand, oh, damn it, I forgot about that. Let's give back and give a look at what is this about, okay? So that we start, everybody starts on the same page. Then I'm going to, after the introduction, so lambda CDM model and the issues with the lambda CDM models, we'll start with dark energy that we already covered during the lectures. I guess that you also covered during the lecture of other lecturers. But we are going to go in more details. Because last semester you have seen we introduced the simplest model of dark energy that we have, just a scalar field, and then we say there is a potential. Okay, now we are going to give a look in these potentials, because the potential is going to define the very precise model of dark energy. Okay, different potentials gives you different physics and physical behaviors. Okay, so there is going to be a collection of potentials, family of solutions that are popping up from these potentials, and we are going to give a look into that. Okay. After that, I'm going to mention also dark energy coupling with matter, because there are the model that we discussed. If you remember the Lagrangian that we introduced, there was no coupling with the matter component. Okay, so dark matter had its life, for example, or matter in general, baryons and everything had its own life, and there was not interaction with dark energy. Okay, so they were completely decoupled. But there are models in which the two are talking one with each other. So there is a coupling, and one element interacts with the others. Okay, so I'm going to introduce this as well. After having dealt with a little bit of dark energy, we will say, okay, I don't want it anymore. Okay, in the sense that we are not going to talk about anymore of a fluid to explain the accelerated expansion of the universe, but we are going to use modified gravity. Okay, because you remember that using GR, we need the cosmological constant, so still within GR, we know that there are issues, that's why people try to set the cosmological constant to 0 and use dark energy. But again, people is not satisfied or introducing dark energy and say maybe it's just GR is not complete. There are parts which are missing. And the people modified GR, so there are extension to GR, modification to the gravity sector, which do not need any more dark energy. So the accelerated expansion is due to gravity. So gravity on large scales is repulsive, and this gives the accelerated expansion of our universe. Okay? And we are going to see how, if we don't have a fundamental theory of gravity, such as quantum gravity, the two scenarios are completely degenerate one with each other. We cannot distinguish them, okay? Because they predict exactly the same features. And observationally, you cannot distinguish one with respect to each other. With a fundamental theory, then there are additional hints in observations that would allow you to distinguish one with respect to the other. After having done that, we will start to look into perturbations. So the formation, you know, the structure formation. Therefore, we are going to investigate again structure formation in the light of dark energy. So we are going to give a better look at what is the impact of dark energy and the various models on cosmic structure formation. Okay. Last time we did it in lambda CDM, so now we are going to use dark energy and various models to see what's happening here. We are going to investigate non-linear perturbation theory up to second order. Okay, so we're going to push a little bit the analytical discussion that we did during the lectures up to second order. We don't stop to the first order. And I'm going to recap a few concepts that I already gave you at Cosmology last semester that was supposed to be for advanced cosmology. So maybe I will just going to revise them, extend them a bit. Okay. And yeah, and this goes also with nonlinear perturbation theory. We're going to see, for example, Zeldovich approximation or other ways in, to approach the nonlinear structure formations, and then observations. And here we are going into more details, because observations are key if you want to deal with observations in cosmology. So if in your career you want to focus your attention on observations, this is a good place where to look at, so where to start and get a grip of the devils that are in doing real observation in all the details, okay? Because, for example, we went through the correlation function, fine. Now you know how the correlation function for the distribution of galaxies looks like, how to deal with it, what's the meaning, how it's linked to observations, but there are caveats, okay? So we are going to look into those details. And if you are not interested in observations, because I'm a theorist, I just want to do my computation stuff, then you still need observations. Because if you don't understand nature, then you're starting to go in the wrong direction. You can build up beautiful theory based on nothing, okay? So you need to understand that. And to make it clear, here is an example where a few years back, people used the Hubble Space Telescope. You see, Hubble, that's the space telescope that we have at hand, still living and observing in low orbits around the Earth. And they perform weak lensing measurements and strong lensing measurements of these galaxy clusters. So we went through gravitational lensing, right? So you are the observer. We have a galaxy cluster along the line of sight, which you can see, for example, here, the galaxies that are populating the galaxy cluster. There is the dark matter that you cannot observe, okay, not directly, but there are background galaxies. And these background galaxies, the photons of these background galaxies are traveling across the space-time, and the galaxy cluster along the way distorts the space-time, right? The metric is not Minkowski, well, the universe is also expanding, so it's not Minkowski on itself, but still there are local perturbations, and the photons follow the geodesics that are curved, and therefore their images, so the photons that we see, those are the images, are kind of a little bit tilted in a weak, faint way. That's weak gravitational lensing that allows you to constrain the matter distribution of this galaxy cluster in the surroundings, and strong distortions that are observing in the core. I don't know if you can see it here, but there is an arc. An arc here, these are two multiple images of the same galaxy. So the photons of this galaxy, the galaxy here, galaxy cluster here, were traveling in this direction, deflected in your directions, and therefore you see two images, okay? Multiple images due to strong gravitational lensing. Now what these people did, so there are a pile of them, so it was quite a big paper with also big names, so extremely well-recognized scientists, and they came up with this dark matter reconstruction for the galaxy cluster. So they have seen an overdensity in the core, that's expected, and then a ring. So they observed a ring of dark matter surrounding this galaxy cluster. Wow! This made a big splash. So NASA, the ESO, and everybody put it on the web page, press releases, it even went on the newspapers, blah, 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 blah. When I saw the paper, I look at it, I thought, okay, border effects, thrown away, okay? And if you look now in the literature, there are several people that came up with theories to explain this ring. Okay? And they wasted time. So that's why it's important to understand also details of these sort of things. And if you see something weird, such as a ring of dark matter around a galaxy cluster, be excited, so be excited about what you see, but be careful at the same time. And go to speak, for example, to the people who did the observations. Look at the paper and see how the observations were performed. And what these people did was to use a reconstruction technique which was based on Fourier transforms. You know that Fourier transforms works well whenever you decompose a function which has periodic conditions, and assuming an infinite extension, right, of your function, which is not the case because they took a telescope, they made a picture, and the picture is confined. Plus, there are no border conditions. And this, when you do apply a Fourier-based approach to this sort of truncated data with no periodic conditions, you can get this sort of artifacts. Okay, so this is a numerical problem. It is not a ring of dark matter. Okay? And people, for example, also tried to explain without some modified gravity, because there are papers about modified gravity explaining the existence of this ring. There are people also used the standard lambda CDM model, tried to reproduce the a dark matter ring surrounding a galaxy clusters, and they managed. But how? They took two dark matter halos. This is a numerical simulation that we went through, and then they let them collide. Okay? And under certain circumstances, you get the formation of a dark matter ring. But when is this possible? When the two halos are perfectly spherical, when the orbits of the particles within these halos are perfectly circular. Okay? Do you believe that something like this happens? No, exactly. So, yeah, okay. Let's say that you can discard these sort of things, even if it was on the newspaper and there were press release about it and so on and so forth. Okay? There are also other examples, but this is one that I liked. And I brought up this example to a talk that I gave at ITP, also, you know, to explain, look, be careful with observation and so on. And then at the end of then I present also other stuff and so on. So there were questions about that, and then very many questions about this ring. Yeah, but what if no, look, this is the bad example. You should not even look at it. Yeah, but modify gravity and the interactions and blah, blah, blah. Okay? So there is when you see something weird, you are attracted, okay? Because it's weird, it's fascinating, but be careful, okay? And that's important when you're going to choose the papers that you're going to read, okay? Good. That's it for now. Any questions? Any question? Okay, good. So we can start now with a recap of cosmology. Okay, so we will start just with the... Have you done GR? Who went through GR? You did GR, okay, then. Yeah, that's fine, that's fine. Should be enough. I mean, that you just need to know the concept, so that's okay. And the equations that I'm going to discuss. So what I'm going to show at the board, you should be able to understand. Okay, good. So let's start to describe our universe. As you know, our universe is vast, okay? And we need to describe its properties on extremely large scales. And on extremely large scales, we basically do not care about interactions and forces that are acting on extremely short scales. For example, the weak force, for example, we don't care because it's acting on an atomic scale, so we don't care on nuclei, we don't care about that. We need long distance forces. Long distance forces which are gravity or electromagnetism. Okay? But on large scales, the universe is neutral. And therefore, electromagnetism is not a relevant force to account for if you want to describe the dynamics of the universe, but what is relevant is only gravity. And our favorite theory of gravity is general relativity. Okay? The covariant theory, it has all the ingredients that it needs. It has extremely strong support from observations performed on the ground with satellites by observing astrophysical objects and so on and so forth. For example, gravitational waves that have been detected, predicted by general relativity, and so on and so forth. So it's a very strong theory, and it's our favorite in starting playground. Okay? So for GR, basically, we need the goal of GR is to explain the behavior of gravity through the space-time, to the properties of the space-time, which are described, in this case, in terms of a metric. Okay? And therefore, we have this tensor field, which we need to understand. We need to understand what is the relationship between the energy momentum tensor that describes fluids, radiation, and whatever, with the gravitational component, meaning the properties of the metric. Okay? So the theory starts with its own Lagrangian. That's the Hilbert Lagrangian that you should know, which is the simplest Lagrangian that lead us to a theory, so field equations that are up to second order with respect to derivatives of the metric. Okay? And it contains the Ricci scalar. And then we have the square root of minus the determinant of the metric, and then our 4 interval size, which is the x0, 0, the x1, the x2, the x3. And this guy is needed, right, to keep this guy invariant, right? R is a scalar, therefore is invariant. Therefore, the action is invariant as we wish. And the Ricci square contains derivative of the metric up to second order. Okay? So with this action, if we want to identify the equation of motion, to find, if we want to find out what are the equation of motion, then we apply the least action principle. So we compute the variation of this metric that lead us to R mu nu minus R G mu nu, there is 1/2, minus 1/2, and then we have the variation of the metric, G mu nu, and then again our invariant volume element. And this guy, because of the least action principle, the equation of motion is the one satisfying this condition. The variation of the action is equal to 0. This is not relevant. Find the 0. This has to be arbitrary, so it's not necessarily 0. Therefore, we need something which is this integral for any intervals that we're going to choose for our integral has to be equal to 0, and that's this guy here. Okay? So for our field equations, in vacuum is going to be like that. Well, we are going to define this tensorial object as the Einstein tensor, and this has to be equal to 0. So this guy has to be equal to 0 to satisfy the least action principle. These are Einstein field equations in vacuum. There is not a source. But we know that our universe is not empty. I mean, we exist. There is not only the vacuum, and therefore we need a source term. Okay, source term that has to be introduced by enriching by introducing a new term in the action describing our system. So our new action will contain the Hilbert action, that's the component of the vacuum that we had there, plus a term that is associated to matter, in front of which we need a constant that tunes the strength of the interaction between the geometric term, which is given by the Hilbert action, so the gravity term only, and the matter distribution. Okay, this makes the tuning. When I speak about matter, and I'm going to use this big M, it's not only baryons or dark matter or this sort of stuff. Okay, could also be electromagnetic waves, could also be photons. Okay, anything which can be expressed through an energy momentum tensor. Okay. Matter is all of that, okay, with the big M. If we now do exactly the same business, so we apply the least action to the total action, then we are going to add the variation of SH plus alpha MSM, and is going to lead us through some computation that I'm not going to repeat here, is going to give us G mu nu plus alpha matter, and then we have that's the derivative of the Lagrangian describing the matter term, square root of minus G over square root of minus G, and then we have the derivation done with respect to G mu nu. And then we have the variation of G mu nu, and then the invariant volume element, square root of minus G, the omega. And again, we impose this quantity to be equal to 0 to satisfy the least action principle. Okay? With that, I can continue like this for a bit. With that, we identify a new term, which is the energy momentum tensor, T mu nu, which is equal to that stuff there. So that's minus 2 square root of minus G, then the derivative of the Lagrangian of the matter component, minus square root of G, over the derived with respect to G mu mu. And the energy momentum tensor written in this way is automatically symmetric. Okay, there is also another way that I also showed you in the past lectures last semester to express the energy momentum tensor that I'm going to show you again, but that one is not guaranteed to be symmetric. You need to symmetrize it. Okay, this one is guaranteed, when you build it up in this way, is guaranteed to be symmetric. And there is also another way to express it, not in terms of the Lagrangian, but in terms of the action of the matter component. Just report it here so that you have this as well. Okay. With that, then we have that this guy has to be equal to 0. So we have minus a constant and the energy momentum tensor equal to 0. For our Einstein fields equations become, well, it's very compact, so I can write it here, is going to be G mu nu equal, now we can identify the constant alpha for the matter component once we impose general relativity to reproduce also Newtonian gravity. Okay, in the weak field limit, you can express general relativity in the weak field limit, and you want, in the end, that this constant is such that Newtonian gravity is respected. Okay, so this sets the strength of your gravitational force, or in this case, space-time distortion. And these are going to be your field equations. So we are going to have, again, the same tensor that contains all the geometrical terms, and the source term, which is expressed in terms of the energy momentum tensor of the matter, again, which is anything that it can be expressed in terms of an energy momentum tensor, or a collection of different things, okay, as we are going to see as well. Okay, good. Then, that's not all, because this equation alone originally had to be modified to keep our universe static. That's why Einstein introduced the cosmological constant. He was allowed to introduce another term in this term, which is linear with respect to the metric, to derivative of linear with respect to derivative of the metric. So is a general relativity allowed that? Okay, it satisfied energy conservations and all the things that we want this theory to work for. But for the wrong reason. Okay, she wanted the universe to be static because at the time they believed, or they had the conviction that the universe was not nor expanding nor contracting. It was kind of sitting like that. Okay, knowing that this is an issue because it's extremely unstable, because just a little kick, a little in, or initial conditions that are not tuned in the right way, and the universe will collapse or expand. Okay. So for years, we have done cosmology without this cosmological constant, because once Hubble showed, look guys, the universe is expanding, then was set to 0. And from the 20s, the cosmological constant was 0 up to the 90s, where, through observations performed with supernovae, so measuring luminosity distances, they realized the fact, guys, look, the universe is expanding, yes, this we knew, but in an accelerated way. The expansion is faster and faster. Oh, we need a cosmological constant, because this guy is able to explain the acceleration of our universe. Using the cosmological constant, we have our lambda model, okay? That then becomes the lambda CDM model when we are filling our universe with cold dark matter, lambda CDM, okay? But we will arrive at the CDM later. Now we have the lambda. So we have our expansion to explain, and we explain it with lambda, okay? We make our theory a little bit more general. And therefore, our action now is becoming, so like the one before, but we are going to introduce the cosmological constant lambda, okay? Of course, then you have your action for the matter component. Oops. Let's make the volume invariant, so like that, and plus we have our action, so we have our Sm and then Sm. Okay, least action principle, blah blah blah, same story, and we arrive at the Einstein field equations that now also contains, so this will be our Einstein tensor, and now also contains the cosmological constant G mu nu, and then we have our source term A pi G over C to the power of 4 T mu nu. Now this explains our observations. Okay? Nice. Another thing that can be done, well, they can be reformulated in a different way, but we will see that later. Okay? Another important concept that we need from general relativity, and several times is overlooked, is to understand energy conservation in a theory in which the metric is might be a time evolution, for example. Okay? Energy conservation, which took a while for Einstein to grab, and to Hilbert as well. Okay, so they managed to solve their issue in understanding energy conservation in the framework of general relativity once Emmy Noether came in to help and understood the origins of conservation laws in physics in general. Okay, so she was quite radical and solved the problem for everyone. Good. So what we get here? Well, conservation of energy, actually the energy momentum conservation, so let me complete that, momentum conservation, is intrinsic in GR. That's because it's a diffeomorphic theory, okay? It's diffeomorphism invariant, meaning you can change your frame and the theory is going to work, okay? You're going to get the very same physical phenomenon regardless of the frame of your choice, okay? So you can apply a diffeomorphism arbitrarily, okay? Good. And to see that, one can look at the variation of your metric, apply a diffeomorphism to your metric, and after a little bit of mathematics, you end up with something which is of a vectorial, written like this is a terms which is a one-form-like object. Then you have your covariance matrix and your term which pops up here after the reshuffling of this term is going to be equal to that, which, guess what? Minus G, the omega, is the energy momentum tensor. Okay? So the equation of motion for the matter component must be satisfied as well, which means that this guy must be equal to 0 as well. Using the definition of our energy momentum tensor, which is, where is it? Down up here, okay, you see. This tells us that the covariance derivative of A, T, AB, well, let's use Greek indices. So I wrote AB, but this is, these are 4. So B goes from 0, 1, 2, 3, okay? So T, blah, 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 mu equal to 0. So this expression pops up by the fact that the action, so this basically pop up from the very same construction that we had for GR, okay? Energy conservation. This has, you see that we are substituting now the standard energy conservation that you are used to in special relativity, which has the standard derivatives. Now we have a covariant derivative, and this has a twist, give a twist to the energy conservation. Because, for example, if our metric is evolving as a function of time, this, for example, the energy of photons in the universe is not conserved. Okay? You have your photon that is traveling across the universe. The universe is expanding, therefore there is a time evolution in your metric, which enters here. And if you look at the standard conservation of energy, which is sort of related to local frames, which could be expressed in this term, well, that's different than zero. The photons do not have the same energy. You have your photon, you get redder and redder as the universe is expanding. Okay? So this is a more intrinsic way to understand the cosmological redshift. You can think, galaxies are going away, Doppler effect, and therefore they are redder. Okay? But the very reason the energy is changing is because of this covariant derivative and the fact that the metric has a time evolution component. Okay? It evolves as a function of time. Okay? Just to have a look at this point before I wipe out everything. I just express the covariant derivative in a more explicit form that contains also this term. Okay? And our covariant derivative, the mu t mu nu, so again you can see the repeated index that we had. So let's use it the same, nu, mu, nu, so that's the same. So that's exactly that very same expression. That is equal to minus square root of g, derivative with respect to nu, of minus, or square root of minus g, t mu nu, plus, then we have the Christoffel symbols, mu, t gamma, nu, with this dummy index, and that's equal to 0. Now you can see that here we have this product. We can use the product rule for derivative, and we will get a term, the nu of t mu nu. This guy here. But there are also other terms, which are non-zero. The photons are changing energy as the universe is expanding. So, for example, cosmological redshift. Not only that, we have seen also other effects that are associated, that can be observed on the cosmic microwave background, one of which is the Sachs and Wolf effect. The other one, for example, is the Rees-Shama effect. Okay, that we have seen when we studied the cosmic microwave background. And again, they are due to the fact that the universe, that the metric is changing as a function of time. This one is due to the background evolution, so the background given by our describing the universe on a whole is changing as a function of time. These things here are sort of more local, okay? So this one is due, so the Sachs-Wolf effect can also be due to the presence of when dark energy, lambda is starting to be relevant, or the Rees-Shama effect can be due to the fact that there is a local overdensity, for example, a galaxy cluster, which is forming, so you see that you have a collapsing object, therefore the metric locally is changing as a function of time. The energy of the photons is changing, is affected. If the galaxy cluster is in this location and is moving in this direction, first the potential was large here, the galaxy cluster moving in this direction, the potential is dropping. Whereas here is rising. Well, actually, it's negative, so it goes the way around. Okay, here it goes to 0, here you get negative and negative as the galaxy cluster is approaching. Again, a local time evolution of your metric. Okay, again, an effect which is impacting the photons. Okay, nice. That's what you basically need to know about general relativity. Okay, so very, very few concepts. perhaps in the lectures I'm going to perform the scalar vector tensor decomposition of the metric, SVT, so it's called SVT decomposition of the metric, that allows you to investigate better the components of your metric in presence of this scalar, vector, and tensorial modes in your metric, okay? In a cosmological constants. In the GR lectures, you have done it. If you have done this sort of decomposition, you didn't introduce the evolution of the background, which is evolving due to the presence of matter, radiation, lambda, or the dark energy. Okay, so we are going to do that as well. So super fast recap about that, even if it's not needed. So we need GR to explain the our universe on extremely large scales, because gravity is the only force that can act also on neutral matter, that is acting on a neutral universe on large scales. That is relevant because it acts on long distances. It's described through the Hilbert action, which is the simplest action that we can possibly use in a theory of gravity which is based on differential geometry. Ricci scalar, which contains derivative of the metric up to second order. Okay, not second order even, but up to, which allow us, which give us the freedom to introduce the cosmological constant as we did later. Okay, so this would be least action principle. You get your Einstein equation in vacuum. Okay, nice, but not enough, because we are not in vacuum. We exist, galaxies exist, dark matter exists, blah blah blah. So we need to enrich our action with another term. The action, which is representing the matter component. And again, this is jargon. Matter, in this case, it can be also radiation, okay? Not just baryons or dark matter. So last action principle, blah, 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 and we arrive at the Einstein field equations, which contains this new term. This new term is the energy momentum tensor. And Einstein field equations acquire this form, okay? A geometric component and the source term, which is given by our T mu tensor. As we said, we have the freedom to introduce elements that are lower with respect to derivatives. So in this case, would be a zero derivative of the metric, which is multiplied by a constant, so that to tune its relevance in our theory, in our universe. And again, least action principle, so you see we are just modifying our action in this way, lead us to this extended field equations, which contains the cosmological constant that we need to explain the expansion of the universe. If we don't use this guy here, then we need to modify the energy momentum tensor through dark energy, okay? But lambda is working brilliantly. All observations so far are extremely well represented by the cosmological constant. Then, another important concept to understand is the conservation laws in general relativity that pops up, is written in this form, and pops up basically by the very inner nature of general relativity. Okay? So these are just the key concepts. Then if we are going to do that sort of decomposition, the dimension, and so on, we are going to go back to the mathematics and see what are the steps to perform that sort of the composition. That, for example, we will do it in a cosmological context, and will allow you, for example, to investigate gravitational waves in an expanding universe. Okay? That can be used. Now the there is the attempt to use them to constrain cosmology, because we have now, for example, the supernovae as standard candles, right, to constrain cosmology through the luminosity distance, but the gravitational radiation, which is carried by our gravitational waves, is a source of, not of light, but of perturbation in the metric, that are called standard sirens. Okay, we sort of hear them in the sense that they are, is a sort of vibration of the space-time, so just to distinguish them from electromagnetically based observations, like, for example, the supernovae. Okay, and again, there is the attempt to use them to constrain the cosmological parameters. Okay, nice. So we can have a little break. So I can wipe up the board. We can resume at 15 past midday. And we will continue then with our lambda CDM model, just a fast recap, plus some enrichment, okay, with respect to what we have seen during the past semester. Okay.